Rider on a merry-go-round is traveling at a constant speed of 4 meters per second and completes 3 revolutions in 14 seconds. In our table, we have time, angular position, angular velocity, and angular acceleration. We also have radial and tangential components for position, velocity, and acceleration. For the radial and tangential components, if you start on page 14 of your textbook, they give you the radial and tangential components for position. The radial component for the position is just equal to the radius. The tangential component for the position is always equal to 0, and this is because of how the radial and tangential directions are defined. So the radial axis is perpendicular to the surface of the circular path, so perpendicular to the tangential direction, pointing radially away from the center, and it goes radially away from the center right to the location of the particle. So when your particle is here, the radial direction is pointed outward here, but by the time your particle moves over here, the radial direction is now pointing this way, and the tangential direction is pointing this way. So your coordinate system is moving with your particle, so the position never has a tangential component. Okay, so we have the radial and tangential components for position. For velocity, the radial component is always equal to 0, because if your object is going in a circle, it's not moving away from the center of the circle, it's not moving towards the center of the circle. If it was doing that, it would be going in a spiral and not in a circle. So if it's going in a circle, the radial component of the velocity must be equal to 0. The tangential component is equal to r times omega. The acceleration is a little bit trickier because it's the tangential component which is related to the angular acceleration. The radial component is always non-zero as long as your object is moving and moving in a circle. So the only way that the radial component is going to be 0 is if the angular velocity is equal to 0. Okay, so we need these definitions to fill out the table. So right away in our table, whenever we are given the radial and tangential components for position and velocity, I can cross out the tangential component for position because it's equal to 0. So just cross that right out. Tangential component is equal to 0. Radial component for velocity is always equal to 0. So cross that out as well. That makes things a little easier for us. Now we're going to read through the problem again. The rider on the merry-go-round is traveling at a constant speed of 4 meters per second. I know this is tangential speed because the radial component is 0, and I know it's speed and not the angular speed because of the units, which are meters per second. It's a constant speed, so that means it is the speed at t1 and also at t2. It completes 3 revolutions in 14 seconds. So we start when time 1 is equal to 0. We end when the time is equal to 14 seconds. And 3 revolutions means the change in angular position is equal to 3 times. For 1 revolution, the change in angular position is 2 pi. So for 3 revolutions, it is 6 pi. So the initial angular position is equal to 0. The final angular position is equal to 6 times pi. And I'm just going to leave it as 6 pi there. And the units are radians. Now, if you really want to know where the rider on the merry-go-round is, the radial and tangential components of the position are only going to tell you the radius. So if you have the radial component of the position and the angular position, then you know exactly where the rider is. I don't know what the radius is, so I can say here this is going to be equal to r, but I still have to figure out what that radius is. If I know the tangential speed, I can find the angular speed because the tangential speed is equal to r times omega, so I know omega is equal to the tangential speed divided by r, but I still don't know what r is, so I can't really do anything with that yet. And then I have a constant speed, if I have a constant speed, the angular acceleration is equal to 0, and it is the tangential component of the acceleration, which is proportional to the angular acceleration. So if the angular acceleration is equal to 0, the tangential component of the acceleration is equal to 0 also. So I can put that in my table. And also, I can use the radial component of the acceleration is equal to negative r times omega squared. So the radial component of the acceleration is equal to negative r times omega squared. And now I have to figure out how to finish filling out my table. Well, I need to draw either a velocity versus time graph or an angular velocity versus time graph. If I do an angular velocity versus time graph, the area underneath the graph is equal to the change in angular position. This is 14 seconds. I don't know what this angular velocity is. I do know it's 4 divided by the radius. Let's just call this 4 divided by r. I do know what the angular position is. The angular position is equal to 6 times pi. So by looking at the area on my graph here, I have 6 pi is equal to 4 meters per second divided by the radius times 14. I can use this to solve for the radius, and I have the radius is equal to 4 times 14 divided by 6 pi, and that gives me a radius of 2.97, and that should be in meters. So I can take that and I can put it in my table. That is 2.97 meters, 2.97 meters. Okay, now notice that if we were to draw a velocity versus time graph, in this case, the area underneath the velocity versus time graph, if you did the tangential component of the velocity, that would not be equal to 2.97. If you did 14 seconds with a velocity of 4, this area is equal to 14 times 4, and that is 56. That is not the radial component of the position. This is in fact equal to r times delta theta. So my suggestion here is just stick with the angular velocity versus time graph, because that makes more sense for us to use. And the slope here is the angular acceleration, which is equal to 0. Okay, which I already knew. The last thing I have to find is the radial component of the acceleration, and I know the radial component of the acceleration is equal to negative r times omega squared. So let's use that to finish filling out the table. So I have negative r is 2.97 meters, times omega squared. Oh, we never found omega. I know omega is equal to Vt divided by r, and now that I know r, I can find omega. So this is 4 meters per second divided by 2.97 meters, and that is equal to 1.35. The meters cancel out, which leaves you with units of 1/2, but this is supposed to be radians per second, and remember that the units of radians come and go for free, so if you need them, you can just stick them in. So this is 1.35 radians per second. This is 1.35 radians per second. Finally, we can put that in here. So this is 1.35 squared. So I get for that negative 5.37. The units for the radius are meters, and the units for omega are radians per second. So this gives you meters times radians squared per second squared, but we don't want the radians in there, so we can just throw them away, and that leaves us with units of meters per second squared for the radial component of acceleration. So this is negative 5.37 meters per second squared. This is negative 5.37 meters per second squared. And as long as your velocity at event 1 is equal to event 2, your radial component for acceleration for event 1 should be the same as what we have for event 2.